So I got introduced a little bit before, but as Mike had said, I work on Volatility. I'm also one of the developers of Registry Decoder. I've spoken at a number of conferences before, and as far as my job goes, it's ranged from pure security, source code audits, pen tests, reverse engineering, to more forensics and incident response, which some of those skills obviously still help because reversing is a big part of memory analysis and forensics in general. As far as this talk, what we're going to go through, we're focusing on Android memory forensics, and this is something that sort of has been missed. Obviously, Android isn't even that old as far as forensics goes, but certainly the memory forensics on it is even further behind the disk forensics. And so what we want to talk about is how to acquire memory. That's the first thing you have to do. Then we want to look at analyzing the data structures that are in the kernel, and then we're going to end with with a preview of some volatility functionality that has sort of quietly been released. We've talked about it before, but will be part of a major release, I would say, early next year. So as I said, the first step is acquiring physical memory. We wrote a tool. When I say me, it's Joe Silv, and Vico and I helped him write it. It was part of his master's project. He's another UNO student, former UNO student. And before LiME came, there was really no good tool to do Android memory forensics, to acquire memory, to analyze memory. We wrote a paper on this and published it in Owen Casey's journal. I have it referenced on my last slide as the references, number 2. But the idea was we took all of the current tools for Linux to capture physical memory on Linux, and in this case we're talking about Intel Linux. And we tried to just patch them up a little bit, get them to cross-compile for ARM, but they didn't work at all. There was a bunch of issues that are fully explained in the paper, but the idea was we knew just patching existing tools wasn't going to cut it, and we were going to have to write our own. So Joe took over, as I said, Joe took over LiME. It's now an open source project, and we know that people are using it on real investigations. So just briefly, before LiME was there, some of the problems that you had with Android were, first off, for those who know Linux well, you have the dev-mem device driver, and this lets you get the first 900 megs of RAM, which on the early revisions of Android devices was more than you needed. Most of them had 512 RAM. The problem was not all devices exported dev-mem, and even for the ones that did, it was broken. And it was so broken that no matter what offset you tried to DD dev-mem on, it rebooted the phone. And this is obviously an issue if you're trying to acquire memory because all your evidence just went away. So this wasn't going to work. So then, as I talked about, we tried to take existing tools and make them work. And the way that these work is they create their own device driver that's similar to dev-mem, but then they implement it in the background. One of the big differences is that these tools are able to get all of RAM. So if you're on a real machine that has 8 gigs of RAM, 32 gigs of RAM, however much it is, there's no limit. Some of the problems we faced with this on ARM and on Android was that RAM doesn't start at 0. And so if you look on your Intel machines, you can look at this on Windows, Linux, all operating systems expose the physical memory addresses. They all start at 0, so you can start your RAM capture at byte 0 to however much RAM you have, and you have a RAM dump. The problem with ARM, as we're going to see on the next slide, is it's not like that. The other thing is DD is broken on many of the stock Android ROMs. There's a bug due to sign extension, so you get the wrong offset. And the other issue with this is if you take your normal model of I have a device driver, I'm going to use DD, I'm going to write it out to a network or a USB drive, that's a lot of context switches. And so you go from, say your block size is 1 meg. What has to happen is you tell DD, read 1 meg, it has to call into the kernel to do that. The kernel then has to write that 1 meg back into userland, and then to actually write that to a file, you have to call back into the kernel to write that out. So you have a lot of context switches, and you have too much data being overwritten in memory. You're losing far too much evidence that you want. And in the paper, I don't remember the table off the top of my head, we did a comparison of LiME to the tools that we patched to get working, and we had something where 99% of pages were the same after we had acquired them, but with the other tools it was something only like 85%. So they were losing 15% of free pages, which can have very valuable evidence. Going to check for questions. Okay, so Mike, I don't know if everyone else can see the questions, so I'll just read it. Mike asked, or Mark asked, or if there are any suggestions on learning how to write device drivers in Linux. And I actually got this question in an email the other day from a student. There's a book called Linux Device Drivers. It's a little old, but it's a few years old, but the first 4 chapters are essentially still valuable. They tell you sort of a skeleton driver. They tell you how to debug from within the kernel, and you can also do it from VMware. So really all the device driver at that point is, I think LiME is only a couple hundred lines of code, and it also does some more complicated things that aren't necessary, or aren't necessary in like a basic project. But we'll talk about that later. So I don't know, there's a few books on it. There's also another book called Understanding the Linux Kernel that's a little dated, but most of the information in there is still current. Okay. All right, so where were we? So now, what I wanted to show, as I said, I talked about here that RAM doesn't start at 0. RAM doesn't start at 0 on these ARM machines. And if you look at physical memory, on Linux machines, you have this proc IOMEM file. This is going to exist on every Linux install. And what it does is it shows you the physical memory maps. And I have here bold the ones that we care about, and these are the system RAM ranges. And this is where your RAM is within physical memory. So if you look, we have 1 here and 2 here. Even if we had a working DevMem or a third-party tool that could recreate DevMem and we wanted to pull RAM from this machine, we would have to give DD this as a starting offset. Then we'd have to figure out the size of this range and make that our count and figure out the block size. Then that would get us 1 section of RAM. Then we'd have to do it for this section of RAM. And at that point, we'd have these 2 files that sort of, if you concatenate them together, you kind of have RAM, but there's gaps here. So the addresses aren't even going to line up. So this is something that we certainly wanted to fix in LiME. We looked at some other hardware. This was a few years ago, but when the PS3 let you do Linux, we got memory analysis working on that, and that was horrible. If you had like 4 RAM sticks, you would have 4 of these system RAM entries all over the place. It was pretty confusing, so we wanted something a little better than having to, especially an investigator who's not as comfortable on Linux, having to DD out huge sections of RAM and get all the addresses lined up and stuff like that. So that brings us to LiME. I have the reference here again. It's open source. It's obviously a kernel module. It needs to load in the kernel to read memory. And that's its first advantage is that once it's in the kernel, it only operates in the kernel. It never goes down to user land. You never have to interact with it again. And it has the ability to dump memory either to the SD card or over the network. And when I say network, what I really mean is ADB, which we're going to talk about shortly. And again, the great part of this is there's very little interaction between user land and the kernel. Once you load the kernel module, you don't have to do anything else to get a memory capture. The way LiME works is if we saw that IOMEM output before, and the way that gets enumerated is you have the IOMEM resource structure in memory. This is a C structure. There's a linked list that joins all of those address ranges together. And you simply just walk those looking for ones that are system RAM, and then you acquire them. Obviously, as part of that structure in memory, it tells you the starting and ending address of the physical range, so you know how much to pull out. So this is really simple, and you're not having to try to copy ranges that aren't RAM, because that's going to be put the machine in a very unstable state, potentially reboot it, potentially corrupt information in memory. So LiME is just 3 steps. As I said, it finds where the system RAM ranges are. It then takes those physical addresses and maps them to a virtual address, and then from within the kernel it writes those now what are virtually mapped pages to the disk or the network. And another thing that Joe added that really helps us not overwrite memory is the same page is used over and over again. So every time you do that translation, that's getting copied into the same page. So you really, at most you can lose is 4K of memory compared to gigs of RAM. Okay, let me check for questions. Okay, so Mike C. asked if I read Andrew Hoog's book and if I noticed any inconsistencies. I haven't read the whole book. I actually think I actually just flip through most books on like Amazon Preview. I rarely read a whole book. And I didn't see any memory forensics. The book's also fairly old, so I don't know if it would have covered something like this. So if I missed something, maybe ask a follow-up question, but from flipping through the book, I didn't remember seeing like deep memory forensics on it. So I'll check back to the question in a second. How to use LiME? This is a kernel module, so you have to give it its arguments before it loads. And there's 3 of these. One is the path, which you either give it a. We're going to look at these sample invocations in a minute. But what you have is the path, which is either a file name if it's going to be on the SD card, or a TCP port if you're going to do it over the network. The next option you have is fairly important, and that's the format. And you have 3 choices. Raw, all that does is take all of the system RAM ranges and glue them together. That's, as I said, this is equivalent to if you DD'd the sections out and then catted them together. The next one you have is padded, and if you remember back to I'll just go back to it, our IOMM here, we have 2 system RAM ranges. One ends at 2E7FF, and the next one doesn't start till 3 with a bunch of zeros. So there's a gap there where there's just nothing in memory, but for the addresses to line up, you have to know to skip those, basically. So when you run in the padded mode, what it does is it calculates however much that ranges from the end of one RAM to the next one, and it pads it with zeros. And this helps because we actually had Volatility working on these before, and it was just the zeros help the addresses stay aligned. Otherwise, when you go to read a physical address, it's going to be wrong because the hardware has those pads there that you don't. The next format we have is LiME. And this is the actual LiME format. This was obviously it's named after the tool. And this fixes all the problems with RAM ranges being all over the place and being of variable sizes, because what it does, before each RAM section that it writes out, it prepends a very small header. I think it's only 16 or 20 bytes. But what it has is the physical offset of where that range is, and then the size of it. And then from there, what you can do is, which we're going to talk about, Volatility can read that information to then do analysis on that file. So now instead of just getting this big dump of RAM and you don't know what it is, you're getting this formatted file that tells you exactly where all the ranges are. So in the background, you can very trivially make the addresses line up. And finally, the last option you have is direct I/O, and LiME will try to do this by default, and then most of the time it's not going to work, and so it drops back and doesn't use it. But with this, when you write to the disk, basically it skips going through the kernel, and it just writes directly to the actual, what would be the raw SD card, and again, that's going to save you from overwriting memory that you actually want to recover. All right, so let me see. Okay, so Mike Wilkinson asked, are those memory ranges the same for all versions and all hardware? And the answer is no. It's completely different for every phone. One thing to realize is that it's going to depend on how much RAM your device has. So that's going to change, and it's really specific to almost like the ARM board that it's sitting on. And at that point, you just have to get that out of the memory, or there's also, like, you can look at the data sheets if you were looking at a phone and you just want to know what ranges it are, but you can also just figure it out dynamically in the kernel. Okay, I got another question, which was what causes DIO to work or not. We haven't really maybe Joe has investigated this. I could ask him, but he has a check for it or LiME has a check for it that if it doesn't work, it falls back. I'm not sure. One thing that's weird, writing with direct I/O to an SD card always seemed weird to me. So I don't know if that's why it's bailing out. I guess we could try writing directly to the internal hard drive and see if we have more luck. But I'm really not sure. Okay, I got another question. In my limited test, I found that LiME was a bit slower than padded format, even if there's more data to write on the USB with the padded format. Let me digest that question for a second. Okay, so I don't know why that would be slower. If you have actual test cases of that or performance, that would be interesting to see. I don't know why. The other thing, writing zeros is very cheap, so I don't know. That could be one of the reasons why it's doing it that way, but it shouldn't be slower because it's writing less data. So we've talked about LiME a little bit. We're going to look at how to use it in a second, but one thing I wanted to talk about, because hopefully people are going to listen to this and actually try it out and explore Android forensics, there's some considerations you need to think of when you're doing acquisition. And the first one we're going to talk about is the network. And again, when I said the network, this isn't, or hopefully you're not putting out over wireless networks, certainly not putting out over like 3G or something. This is an ADB port, and what ADB is, the Android debug bridge. And it's when you plug your Android device into a USB port on the computer, if you turn USB debugging on, you can get basically shell access to the phone. And you get what's a limited shell. If the phone's rooted, you can install BusyBox and every other Linux application you can think of on there. But the idea is, with this, you can also set up TCP ports over ADB. So the way LiME works is you open one port on the computer, you tell it the port that is when you load the kernel module, and then it's going to dump all that data to your computer, and it's just going over the USB wire. So you're not, as I said, putting data on an actual network, but you're just very quickly siphoning it through the USB drive to your analysis laptop. Now you're not overwriting data on the phone, and you have your memory dump. The problem with this, as I said, is it requires USB debugging for ADB to work. And if you walk into If you walk into a typical enterprise and you take a phone, an Android phone, where they're using some security product that can put policies on the phone, they're almost all going to have USB debugging disabled, and the policy is also not going to let it be turned back on. So that's a serious problem, because now we can't use ADB, and we basically look at a choice of, do we have the sysadmins push a modified policy to that phone before we acquire from it, or do we just write to the disk? And that leads to the next slide, which is there's more considerations for the disk as well. Obviously, when you take your memory capture to the SD card, you're overwriting unallocated space on it. So your first thought might be, well, let me acquire the SD card first and then do memory. First off, that violates the order of volatility. You want to get your most volatile data first, but even if you were willing to ignore that, on most devices that you look at, the SD card is under the battery. So even if you even if you wanted to take the SD card out, put it back in, and then put your memory capture on it, you have to pull the battery out first. The phone's going to go off, all your volatile evidence is gone. The other thing is, it seems to be a trend in devices, is you can't take the back off at all. And at that point, you have no access to the SD card. If you can't get ADB access, you kind of just have to say, okay, I'm going to write it to the SD card, and I know data is going to be missing. One thing to realize with this is your devices, your Android devices, have anywhere from, say, 512 meg RAM to 2 gigs. There might be devices with more RAM already, or they'll be coming out. And then if you look at your stock SD cards, they're 8 gigs. So if I have 2 gigs of RAM and an 8 gig SD card, and I take my memory capture to the SD card, I've just overwrote a fourth of the card. That's a huge amount of evidence to lose just trying to acquire memory. So hopefully ADB works and you can get access to it. If not, you just have to be aware that you're potentially not recovering much deleted evidence from the SD card. Okay. All right. No more questions. So now we're going to look at how to use LiME in a real case. And what we're looking at first is how to do it the TCP way. So the first thing you're doing is using ADB. So you're on your host analysis machine. You have the Android SDK installed, which is going to install ADB. And you want to take a memory dump of a phone that you're connected to over USB. So you push the kernel module onto the SD card. There's other writable places on the device, but the SD card seems to be where it normally goes. So you push the kernel module into the SD card. You then use ADB to forward the port. In this case, we're forwarding 444 on the phone to 444 on the device over USB. Now what we want to do is get a shell on the phone so we can load the kernel module. We do ADB shell. Now we have a shell on the phone. Obviously the device has to be rooted, so at this point you need to run a local exploit that's going to get your root. If you have a device that's already rooted, you can just run su. Now you're root. From here you can use the insmod, which loads kernel modules, to load LiME. And you're looking at the parameters that we use for this sample, which was our path is TCP with the port that we forwarded and a format of LiME. Now on the host, what you can do, the kernel module is going to be sitting there waiting to dump memory, and then on the host, you netcat to localhost on 444. That, again, is going back over the USB cord to your forwarded port, and you get your memory dump. So it's a few steps, and I might not have explained it the best way, but hopefully it makes sense. The idea is you have your USB cord to a phone, and you're dumping memory over the network, which is really an A to B connection. And all the kernel module is doing is sitting there waiting for you to connect to it, and once you connect to it, it's going to dump RAM to wherever. And in this case, it's netcat, and we're redirecting it to our memory dump. Once this process finished, we'd have a memory dump of the phone in the file called evo.lime. The other option we have is to do this to a hard drive, or the SD card. You can also do this, I guess, to the internal hard drive, but I would not recommend that. They're usually very small, and you really don't want to overwrite unallocated data on the internal drive. So if we're doing this to an SD card, again, we're starting the process over, so we have to push our kernel module onto the device. Now we don't have to forward the port, so we just do ADB shell. We have a shell on the phone. We get root access, and now our path parameter is a path on the file system, which is /SD card dump.lime, and our format's lime. Once this process finishes, this is going to immediately start dumping memory to that file, and when it finishes, we'll have our memory dump on the SD card, and then we can pull that off and start doing our memory analysis. So this is concluding what we're going to talk about with LiME. If you have any questions related to LiME, now would be the time to ask them. You can ask them later, but we're going to be talking about some other topics. And so LiME is currently the most usable memory acquisition tool on Android. We've used it a bunch. We've had emails from people using it. We've had people say it's worked great on a case, and now it's part of their process. So we know it's out there. And I have the link in the references to the LiME page. It has the PDF instructions, help you with cross-compiling it, because that's one thing you have to do is compile the kernel module per phone. This is something that we're working on. Many people in the Forensics community are working on it, but right now you have to compile one kernel module per phone, which is annoying, and especially for people who are not used to dealing with source code, it might not be straightforward. So hopefully the instructions are clear, or what would be even better is if sometime soon we can make it so there was just one version of LiME that would load on any phone, but there's quite a few technical restrictions on that. Okay. Any questions? Okay, so I had a question of integrating the swap file in the LiME format. We haven't really talked about that. That might be something where you'd want to pull the swap file off the phone and then integrate it. The other thing is that Volatility doesn't support working with the swap file right now, so we'd have to add it to LiME and then also integrate that into Volatility. Also, unless I've missed something, I haven't seen many phones that actually use swap, which is maybe why we haven't thought about it too much. Okay, so now what we're going to, hold on, I think maybe there was one more question. Okay. Now what we're going to do is jump from LiME to kernel memory analysis. At this point, we have LiME. It's able to extract physical memory for us, and we won't be able to do something with it besides just running like strings and grep or something like that. So what we did, Volatility already had Linux support when we started this project of dealing with wanting to do Android memory analysis. It's now official as of the latest release, which has been maybe a month or two at this point. But we needed to make it work on ARM, and then we needed to see which of the existing plugins needed to be updated or patched to still work on Android. And again, we published a full paper on this, so read that if it interests you. And to make ARM work, what we needed to do was write an address space for Volatility. And address spaces are Volatility's way of having the internal system mimic or perform the translation of virtual addresses to physical offsets, and then this is what's normally done by your memory management units. So this is how you have paging in virtual memory. But obviously offline we have this physical memory dump. All the interesting things that we want to look at are going to have virtual addresses, so we need to be able to translate between the two. These are specific to each architecture, and this is probably the one part of Volatility that's not very fun to write. Everything else is pretty straightforward, and Volatility helps you out. This involves a lot of staring at architecture manuals, seeing how the pages are laid out, and then writing code to replicate that. And then you have to test it and make sure that for every type of page the architecture has, your code works successfully. So the address spaces that Volatility has, we have Intel 32 and 64-bit. We also have PIE support. We now have ARM support, which will be part of the next release. And those are the memory management ones. We also have address spaces that make it so if you give us a file in a specific format, you don't have to convert it to a raw memory capture before you can analyze it. So these are things like Windows hibernation files, Windows crash dumps, your old version of the encase files. Our Mac support has support for Mac Memory Reader, which is I believe the only tool really in widespread use for getting memory acquisition from Mac machines. And of course we now support LiME as well. So, and when I say LiME, this is that LiME format that prepends the header. So what the address space does, it knows what that header looks like, it knows how to read the data out of it, and then when Volatility says translate this address for me, it knows how to look at that header data and find the right offset. As far as the ARM address space goes, it's in SVN. Again, people are using it right now. It'll be part of the official Volatility release, which will be sometime early next year. And we tested this on as many Android devices as we could get our hands on. And what we found is that as far as Android goes, the devices, ARM has some really crazy paging structures. It's nothing like Intel. And right now we have support for 64K pages, 4K pages, and 1K pages. ARM also has this notion of super pages, which is very complicated, and the issue with this is we've never found an Android device that actually uses them. We have a big warning print message in the address space so that if we find one of these, it's going to tell you something along the lines of super page found, please file a bug report, and then we'll likely need to use your sample to help write it because we can't find one that has it. But as far as the tens of Android devices that we looked at, the ARM address space works really well and can perform full translation. Okay, so I'm going to demo real quick, but I want to see if I had any more questions. No more questions. So what I'm going to show is we're going to look at volatility for the first time. And the first thing I want to look at was those in and out mem maps. And what we see here is this is going to look very similar. By the way, I'll explain the command line. I'm using the profile of an Evo 4G device that we had. This is a memory dump that Joe put together for the DFRWS challenge, and that's just what I'm going to be demoing on. And we have our Linux IOMEM plugin. And this is the idea with this. It should be the same output as if you cat proc IOMEM, which is what we saw on a previous slide. Okay. Is that better? So we ran the IOMEM plugin. We got the address ranges like that we were talking about before. And one thing you'll notice is we had a question before, is it the same on all the phones and devices? This one's completely different than even the other one we looked at. This one has 3 memory ranges. So I just got a message that it's still too small. So let me make it a little bigger. And, okay. And I'm also being told to switch it to black on white. 1 second. Yeah, I'm actually not even sure how to switch the colors. I don't think I've ever done that before. Can everyone read it white on black? Is there problems with it? Okay. All right, so I just got a message that it's okay. All right, so as I said before, we had that phone before where you had 2 system RAM ranges, and this one, if you look here, we have 3. And what this is telling us is the starting physical address and the ending one. So if you remember, one of the points of LiME is to be able to go into memory, find all these system RAM ranges, and then write them out to disk. So what we have is a LiME info plugin. Again, what this is doing, this is looking at the same file where this IOMEM plugin was run, and it's going to tell us the ranges. And, okay, they actually fit perfectly on the screen. So if you look at this one, we have system RAM at 200. This is the same 200 here. The ending address is the same, and if you just kind of look, these are all the same. This is the same addresses that are mapping up here. So this is showing us that LiME indeed found these system RAM ranges and could write them out to disk. The other piece of information we have is the offset. And this is telling us the offset into the file of where to find this. So I don't know how many like programmers are listening, but the idea is if volatility says I need to access physical address, 3 with a bunch of zeros behind it, then LiME knows how to walk this information and say, okay, well, this is where the offset is. Or if there's an address that volatility needs to read between these two, it can say, I know it's here. It figures out the sort of the delta from the start, and then it adds it here. And so from there, the address space can handle any requests for physical memory. And we have this nice LiME format that really helps us out, and it makes the volatility workings much cleaner. Okay. No more questions. So that was just looking at 2 simple plugins. We're going to look at quite a few more as we're going through. And the first analysis type that we want to look at is the idea of processes. And for each process, what we want to be able to see is the name of it, the command line arguments, Linux stores the start time of processes, and then the other information that can help us look at it on the file system and also look at sort of malware attacker activity, which is going to be the process ID, the parent process ID, which is going to let us see what process spawned one, also the user and the group ID, and then we're going to look at the PS tree plugin, which takes the parent ID and the process's PID, and it shows those relationships. And this is interesting because you can see if someone comes in over SSH, well, then its child process is going to be bash. And then if someone's running like a backdoor on the system, its parent's going to be that bash shell. And you can follow kind of the path of attackers by looking at these plugins. And that's something we're going to do in a minute. The other stuff that we're interested in on a per process basis is the open files and what files it has mapped into memory. And this is going to be things like your main executable, any shared library that it needs. This is equivalent to DLLs on Windows. And you also have your non-file backed memory, so your stack and your heap and any other anonymous memory that the process is using. So we're going to look at this now. Let me clear my screen. And we're going to use the PSlist plugin. And because the font's huge, this is going to run a lot. So we'll just look at like the first 10 of them. And, all right. By the way, this is using an old version of Volatility that doesn't handle the pipes well, and it freaks out. So what we have here is the first 10 processes. You have init with the process ID of 1. It's telling the user and the group ID and the start time of the process. So you can see this was like a week or 2 before DFRWS when the challenge started, which is the sample I'm looking at. The other thing we have is the PS tree plugin, and this is going to show those parent-child relationships that I was talking about. So we'll let that run, and then we'll scroll up. And what we see here is init is the first process that's spawned by the kernel. It has PID 1. It's always going to run as root. This then spawns every other userland process. So how the PS tree plugin shows you this is you have init, and then with 1 dot under it, you have all these other processes. And these are your userland processes that are running on the machine. And if we come down a little bit to what I was talking about before to see what an attacker did, we're going to see how the memory dump was actually acquired. We have our ADB daemon. This is the version of ADB running on the phone to take those commands over the USB device. That has 1 dot because it's under init. When you run ADB, if you remember, we were doing ADB shell, so that's going to give us a shell on the phone. And then we used insmod to dump RAM. And so now what we see is that PID 1873 is insmod. And if we use our PSAUX plugin with that PID, we're going to see the fact that we ran insmod, and this is the path that we had. So we had our SD card, the path, and the format. If you're wondering why I specified, oh, here you go, sorry, I was looking. So you have insmod, you have the path to the kernel module, you have the path of the network port, and then you have LiME. So again, this is showing us that you took a memory dump over ADB, and we can trace all of that by looking at those parent-child relationships. We're also going to use that towards the end of the talk to study Dalvik a little bit. Let's see if there's any questions. Translated offset. Okay, I have a question that says, when volatility prints offset key in parentheses, is it the translated offset or the one in the LiME file? And that's going to be the offset into the actual file, because that's actually coming from the results of paging whatever address the data structure is at. So that's going to be a real like physical offset into memory. Okay. I think I'm back to the slides. Oh, okay. So the other thing I wanted to demo now is this idea of the memory map. So we're going to go back to our init process, which we know is PID1, and then we have the proc maps plugin, which shows us the memory maps for, if you don't give it the -p, it'll show it for just every process. You can also give a comma-separated list of process IDs to look at, but we're just going to look at init. And what we see is we have our init binary, we have the heap, and we have the stack. And if you remember, these are non-file-backed memory mappings in the process. So now what we want to do to show the complementary plugin to this, which is dumping maps to disk, say this is like for, say, malware, if we wanted to reverse it, or if we wanted to dump the heap to see what kind of data the application was using, we can use this dump maps plugin. And for this one, to get the actual init binary out of memory, we want the mapping that's readable and executable. That's going to be the binary. This one that's readable and writable and not executable is going to be the data of init. So this is going to be all of its static variables and global data structures. So to use this plugin, what we do is we use our dump map plugin. We give it our starting virtual address that we're interested in. Again, if we don't limit this, it's just going to dump all the addressable memory of that process. And then we have an output file, which can be init demo or something. So it's telling us it's writing this. I don't know why it's taking so long. So we're dumping this entire thing out, which I guess is, it has to dump it a page at a time, which is 4K. All right, there we go. So anyway, it's telling us it wrote over 800,000 bytes, so that's divided by 4K, that's quite a few pages it has to write out. And it's telling us it wrote to our file named init-demo. And if we run the file command on this, which looks at it, we see that this is an ELF32-bit executable for ARM. So what we've done at that point is we've had this init binary in memory. We looked at its process, we dumped it out to disk, and now we can analyze this like as if we pulled that file off of disk. This is also interesting because let's say you have malware that's changing this binary in memory, whether it's overwriting some of the instructions, it's changing some of the static data. That's never going to be reflected on disk. That's only going to be in memory. So now you can pull the binary as it exists out of memory and start doing your binary analysis on it. As I said, the other interesting thing you can do is dump the heap, because that's where all of your global allocation or your global memory allocations for a process are. Okay. Any questions? So we looked a little bit at the functionality that we have per process for Android, and now what we want to do is look at what we can see from the kernel. And we have a few things. One is you can list all the kernel modules. Particularly on Android, you really shouldn't have custom kernel modules. Users shouldn't be loading their own. A legitimate user that's using a stock ROM and doesn't root their phone can't even load kernel modules. You never get root access. The other thing we can get is the debug buffer. If you've ever typed DMESG on the command line, you get what's known the kernel's debug ring buffer. We pull that same buffer out of memory and print it to the command line. The other thing that's in the kernel is the kernel's memory caches, which are known as the kmem cache. And the reason these caches are interesting is because the kernel, for things that are allocated, that can be allocated many times a second, it needs to be able to quickly allocate them without going through the traditional, like looking at a heap or looking at a list, a free list, and getting the data out. So instead, what it does is each cache holds objects of a specified size. In this case, it's going to be whatever the size of the C structure is that it's backing, and it pre-allocates a number of them. So one example is processes. Your process structure is backed by the task struct cache, and if you look in that cache, you're going to get all the processes that are active on the system. If you walk the free list of that cache, you're going to get all the processes that were once allocated but are then deallocated. So this allows us to not only see what objects are currently allocated, but we can also pull some historical data out of the cache. And again, the reason the operating system does this is it's a huge performance it helps with performance. You can't wait, like if you're sending network packets out, you can't wait for some slow allocation algorithm to work. You just need the memory there to store your data. So the caches that are of most interest to us, as I said, you have the process cache. You also have the memory map cache. This is going to show you that output we saw from the proc maps plugin. So you can see all of the libraries that are loaded into memory. You can see all the applications that are loaded into memory. And for the historical ones, even if you're only able to get the name, that's still helpful. Because if you think of shared library attacks, which is where an attacker, let's say I have an Apache process and I want to steal all the input, or I have an SSH process or an SSH daemon process and I want to steal all the user credentials that are typed in. Well, I can write a shared library that does that, load that into the SSH process, and then overwrite the function pointers within that process and have it call into my DLL so they get recorded. This is where being able to pull those old memory mappings out is very helpful, because you're going to get a list of which mappings were there, and something that's like loading out a /temp into the SSH process is going to look very, very suspicious. You also have the file cache, which is kind of the same idea. This stores the files that are opened by processes. So if you kind of baseline your system and then you dump the open file cache, anything that wasn't in your baseline that was open means it was created after you did the baseline. So you can see, okay, was it just a user creating a file? Was it a log file for a rootkit? But you can filter out your known good data very quickly this way. Any questions? The next capability I want to talk about was recovering networking information. The first one we have that's very important in things like data exfiltration or attackers jumping around the network is being able to recover the ARC table, because this is going to show you which machines the device that you're pulling memory from recently communicated with. And this is a good example of something that's never written to disk. So if you don't do memory analysis, you're not going to find it. Your only hope might be looking at like a network capture if you have it. The other thing we have is replicating ifconfig, which is going to show you all the interfaces. We're going to look at that output in a second. We can also recover the routing cache, which shows the idea of the routing cache is when you talk to a server outside of your local network, your operating system has to figure out the best route to get there. And so what it wants to do, instead of having to do that every time, it builds a cache of the best route to the destination IP address. So by pulling the routing cache out of memory, you can see all of the external IP addresses that a machine was talking to. So in this case, if you downloaded something off the Google market, we'd see that you talk to the Google servers. If you're using the web browser, we would see all of the websites that you communicated with. We also have the ability to replicate the netstat command, and another interesting thing is we can recover the per socket packet queues, and this is going to take a little bit of explanation. So the idea with this is, let's say you have a server running, and you have your server running, say it's an FTP server, it's reading in data over the network, but let's say the data is coming in faster than the server can process. All of the packets that have made it to the machine but not processed by the daemon are going to be sitting in these packet queues in the kernel. And what the Volatility plugin can do is then enumerate every socket that's on the machine and pull those packet queues out. So now you know data that's coming into the system. So an example for a phone might be, let's say I'm downloading a big file over 3G. My application, your browser isn't going to be able to keep up with that download, so you're going to have information within the kernel. So now I can pull pieces of information out of a file you were downloading. It also works the other way. Let's say I'm exfiltrating data with an FTP client, or I'm uploading it with my browser, or I'm sending it over email. Your connection to the internet is never going to be as fast as your client can produce those packets. So all of those packets then sit in the kernel in a queue until they're ready to be sent out. So again, what this plugin can do is enumerate every socket, look at the send queues, and then dump those to disk. And this is really interesting because it's very hard for someone to say, oh, I wasn't exfiltrating that file, or I wasn't sending that file outside the network, when it's sitting in a very structured packet queue within their operating system. And the other thing is, if you have network captures on your network, then you can say, okay, well, we saw you transfer this much of the file, and the rest of the file was in the memory of, say, from your browser process. It's going to be very hard to argue out of that. So I just got a question that says, is there a standard queue size? I don't think there's a standard queue size, mostly because the size of data that gets transferred is so the size of data that gets transferred is so variable that I don't know what kind of queue they could make that would sort of flow with a normal user. The other thing that's interesting is these are backed by the K-mem cache, so even if you can't find the process that it links to, you can still recover the fact that the packet went out. So I don't think there's a queue size, mostly just because they get allocated out of the cache. So the kernel is going to pre-allocate a number of these structures and then just sort of hand them off to processes when they want to deal with the network. So I wanted to show ifconfig real quick. I'm sure most people that use Linux or investigate Linux have some idea what this normally looks like, but it looks quite different on Android. It also looks quite different on iPhone for similar reasons. So what we have here is your normal desktop, laptop running Linux might have 2 or 3 devices. They have your local address, which is your localhost interface. Depending on how your kernel is compiled, you might have this dummy driver. But then besides that, you might have an Ethernet adapter and maybe a wireless adapter. So at most, you're going to have 4 interfaces. Android's way different. I'm not even sure what these are, but I know the ARMnet interfaces are if you're sending data over like 3G or 4G. This comes into play. It's pretty obvious if you're using USB. And the other thing is your ETH0 interfaces or ETH1 is always going to be your wireless adapter, your wireless card that's inside the phone. So just looking at the output of this plugin, I can say fairly certain that this guy was not connected to any sort of provider network, and he was connected to a wireless network. So that's interesting to be able to know if you want to then further your investigation. Okay, the next thing we have is the ability to analyze mounted file systems. And this is pretty straightforward. It's usually not that interesting, but Android has some interesting artifacts. And the first one is if you see /system mounted as read-write, that almost 100% signifies that the device is rooted. /system is normally mounted read-only, and so the rootkits, or not the rootkits, if you download like a one-click package that says, if you run me, I'll root your device and be able to install these packages on it. If you look at the bash script that those kick off, one of the things they always have to do is remount the system partition read-write so that they can actually write to it, because that's where applications are stored and that's where some other data is stored that they need to be able to add to or modify. So again, if you see /system as read-write, you're dealing with a device that's currently rooted or that was rooted. The other thing that's interesting is Android uses many tempfs file systems, which we're going to look at. And Android also provides this thing which is secure mount points on the SD card. And the idea is normally when you store data on an SD card, it's unencrypted. Anyone that takes the SD card can read it. So they wanted to be able to provide something where applications could encrypt their data. And this is the notion of Android Secure, which becomes a folder on your SD card that the operating system controls, and any data being written there is encrypted. The other thing we can do, which is related, is files and entire file systems can be recovered directly from memory. And we're going to look at this in a second. But even without the disk, if you have your memory capture, you can recover a large majority of the files, depending how big the disk is and what files are being read and what files are actually in memory. So for many investigations, if I'm looking at something particularly IR related, you don't even need the disk. You can just pull the files out of memory. Another interesting aspect of this is if you have an encrypted disk or an encrypted file, the file in memory is going to be unencrypted so that the application can actually do something with it. So if you pull that file out of memory, you don't even have to worry about decrypting the disk or decrypting the file because it's just in memory for you. The other thing that we're going to talk about now is this idea of tempfs, which is a file system that exists only in memory. So if you turn the phone off and then you image, say, the NAND or the SD card and you don't take your memory capture, there's going to be evidence that you're just necessarily going to miss because it's never written to the disk. And Android uses tempfs in a few interesting ways. The first one is the application cache is stored as tempfs, and if you use the stock browser on Android, and I believe potentially Chrome, I need to look at it again, their browser cache is stored as tempfs. And this kind of makes sense because one thing it means when the phone reboots, your cache goes away, but the other thing is that RAM is much faster than disk. And so when you want to look at a page again, or you need to look at a file that's already been downloaded, the operating system in the browser can read it out of memory much faster than trying to go back to the disk. And the other thing is part of that Android secure infrastructure that I was talking about operates through tempfs. So now what I want to do is actually look at recovering tempfs from memory and see kind of the power that this gives you, particularly when you're looking at Android devices. So this is done through the tempfs plugin, and you need to run it first with -L, and this is going to list all of the tempfs file systems that are in memory. And now what we see is it's giving us basically a list. These numbers don't really mean anything, the plugin just generates them, but it's saying the first one is app cache, you have your Android secure mount, and then as you would expect you have your /dev. That's the same you would see on any Linux system. So now what I want to do is recover this app cache directory. So I'm going to make something, we'll make a directory that we can write to. We use the S flag to pick which file system we want, which in this case is app cache, and then the D flag is the name of a directory that is hopefully empty that we're going to recover the file system to. So again, this is going to take a few seconds because it's enumerating the file system in memory. It's finding all of the file contents, which in memory is stored one page at a time, so it's 4K, and then it has to write those out to disk. So this is done. If we want to get some idea of what it recovered, we can look at the directories that are there. And we see that we have this SIC thing, which you may, or CIQ, which you may have heard of. There was a big privacy issue with it. But as I said, your stock browser is also going to write its cache. And again, what this plugin did is it took that file system in memory and dumped it completely out to disk. There's no on-disk representation of this file system, so if you didn't have a plugin like this or something that could do the same thing, you would never find this evidence. So now if we ls this directory, we see that there's quite a few files. We had 68 files in the browser cache, and if you run file on them, and we'll just look at the first couple, we want to run it on all the files in that directory. We see that we have real files. So we have some GIF images, we have some JPEGs, we have an HTML document. So again, we've pulled the browser cache directly out of memory, and that's the only place it exists for the stock Android browser. So this is something you want to do. One plugin that I'm not really going to spend much time with in this demo is the Find File plugin. And what this one is, if you know a path to a file on disk and you want to try to recover it from memory, you can simply give it that path and it'll pull it out to disk. So it doesn't have to be on a tempfs file system. It can be on any file system that Linux supports. Another capability that we have is the ability to detect rootkits in memory. One of the most important ones is finding hidden processes, because that immediately tells you that the system's compromised, and if you can find the structures for that process, then you can get a good idea of what the rootkit was doing. So we have the Linux PSView. This should be PSXView plugin. It stands for cross-view, and what that does is we have the ability to gather processes from a number of places in the kernel. We have the kernel's process list, we have the process hash table, and then we also have that kmem cache that stores process structures. And we enumerate all of those, and then we report which processes show up in which ones. And so if you have a process that's, say, not in the process list, but it's in the process hash table, that means the rootkit hid that process and didn't want you to be able to see it. Something to think about with this is you may say, okay, well, what if the rootkit hides from everything? Just in my own experience, I've never seen a rootkit that hides from the PID hash table, and hiding from the kmem cache I would rate as extremely difficult, or you're just not feasible. You're not going to do it. So this is a pretty strong way of finding hidden processes. And if you look, we have sort of complementary plugins against the different operating systems we support. If you look at the latest version of the PS Crossview plugin for Windows, it actually checks like 9 or 10 places in memory for process lists, and then it tells you where they are. So you may say I can hide from 3 things on Windows, but it's going to be fairly infeasible to hide from that many places on a Windows system. The other ability we have is finding hook data structures, and this is important because what do I classify as sort of your simple or your lame rootkits are going to just overwrite some coded memory, or maybe they'll just hook the system call table. That's very trivial to detect. That's static data. You can build a profile of it just on disk with the kernel, having the kernel on disk. But the more interesting part and the more challenging thing to do when detecting rootkits is finding rootkits that change dynamic data. And we have a number of plugins that do that for Linux. The first one is checking network data. So if you've ever explored under /proc on Linux, all of those files, when you read them, when you write them, they go through the same interface. And so what rootkit authors have figured out is if they hook the reading and writing of those files, they can hide a huge amount of data from user land or from a sysadmin who's running netstat or running PS, or maybe they're actually looking under proc themselves. But a rootkit can trivially hide that. So what the first plugin does is it looks at all those structures relating to network connections, and it prints any of them that are hooked. And these are for rootkits that want to hide from netstat, for example. The other one we have checks the file operation structures, and these are the structures that anytime you read to a file, write a file, close a file, any interactions with a file goes through these structures. And again, rootkits can hide files that are there. They can lie about the contents of files if they have these hooked. So we want to be able to find all of these data structures in memory and then verify them. And the last one we have is checking the kernel modules. So the way this works is rootkits want to be able to hide from lsmod. That's a very simple way just to see modules that are on the system, and that's going to stand. Any foreign modules are going to stand out pretty clearly to a sysadmin. The other thing is we have the Linux lsmod plugin that just walks that list and prints what's there. It doesn't try to do any rootkit detection because the check modules plugin is for that. And the way this plugin works is it walks the kernel modules list, and then it also walks the list of kernel modules that sysfs knows about, and it compares them. And at that point, if there's a module in sysfs but not in the kernel module list, then something's wrong, and something was trying to hide that kernel module. I wrote about this plugin when we did the month of volatility plugins, maybe 2 months ago, 3 months ago, however long ago it was. I had never seen a kernel module hide from sysfs before, and about a week later after I did the blog post, I saw someone do a write-up on how to hide from sysfs too. So that's kind of one thing when you reveal how you're finding rootkits, they're going to find a way to get around your new techniques. Okay, so are there any questions before I move on again? We've looked at analyzing data within kernel memory, but now what I want to talk about for the last few minutes is this idea of looking at application-specific memory, which is a little bit different. So as I said, everything we just talked about is in the kernel. And why this is helpful, obviously we talked a little bit about all of the information that's there. There's a lot that we didn't talk about. It still doesn't help you too much if you want to pick one particular application and then analyze it. And this is useful because, as we're going to look at, I'm sure most people know there's malicious Android applications. Those don't have to do anything in the kernel to wreak havoc on your phone, to steal files, to exfiltrate files, to send text messages that are going to charge you some rate, to destroy your data. They don't have to do anything in the kernel. All they need to be is an Android application that can root your phone or that leverages your already rooted phone basically to do what it wants. So to fix this discrepancy on Android, what we're working on right now, and as I said, should be released at some point, hopefully before, or within an official release sometime before next summer, it'll be an SVN well before that, is this idea of Dalvik analysis. And Dalvik is Google's, what would basically be a re-implementation or a clone of Java. There's some funny write-ups in the big case when Oracle sued them for basically ripping off Java. It showed an extreme lack of technical skills on part of the lawyers, which I found humorous. But it's hard. Dalvik in most cases is basically just a re-implementation of Java. So if you can read Java, if you can develop in Java, you pretty much understand Dalvik. And this is so important to us because every Android application is powered by Dalvik. So if we want to be able to pick on a particular Android application and analyze it in memory, we have to be able to first analyze Dalvik. And the way this works is every process gets its own instance of the Dalvik VM. This is equivalent to every Java instance on your desktop that you spawn is going to have its own JRE. And there's some interesting stuff here, though. We could do probably a whole talk on it. I'm going to try to get through in a few minutes. But every process gets its own instance of Dalvik. And the way this works is the operating system, if you have 100 applications running, doesn't want all of those libraries and the entire VM being put into each process. That's a huge waste of memory. You're obviously resource constrained on a phone compared to like a traditional desktop, and you also have to put into consideration like battery usage. So the way Google decided to do this is you have this process called the Zygote process. That's what it's going to show up as. It's really the app process on disk if you wanted to like reverse it, or it's open source if you wanted to read the source code. You're not going to find like a Zygote process. Look for the app process one. And the virtual machine is encapsulated within a shared library called libdvm. Obviously, it's lib Dalvik virtual machine. This is written mostly in C. At this point, I've read most of the source code for it. And this is basically your JRE. This is what's controlling all of your classes in memory, your objects, your garbage collector. It's all being controlled or directly implemented within the shared library. And again, the point of this, what we're going to look at now, is kind of how this works, because it's not immediately clear when you start looking at Dalvik applications in memory how they actually function. So what we want to first do is look at the Zygote process and then take that all the way down to individual applications and see how they operate. So what we want to do is run our PSList plugin. And we want to look for the Zygote process. So we get this back, we get the process ID and the start time, and now we want to look at its memory mappings, because we want to figure out this process is supposedly spawning everything that all of the applications, so we want to see what's there. And if we do this, I'll pipe it to a file because we have small resolution. We'll pipe this to a file because there's a bunch of them, and the resolution's pretty small at this point. So what this is doing, obviously this is going to have more than just the init process. It's the entire Dalvik virtual machine has to be kicked off from here. But one thing that you notice is if you look for APK files, which is how your applications are packaged on Android, there's not too many of them. All you have is the base framework and this HTC resources. As I said, we're looking at an Evo. HTC has the ability to customize this a bit. But one thing that's strange is that you really just have the core framework within the Zygote process. So if we go back to if we go back to our PS tree output, where we see those relationships between the processes, we see that we have the Zygote process, which is under init, and the first process under the Zygote with the 2 dots is system server. And this is where the work actually happens of making sure that libraries are shared across process address spaces, so that the Dalvik VM is shared across it to an extent. Obviously, once some data is changed, then that the particular application owns those changes, but you don't want the full-blown memory maps in every process. So if we look at system server now, this is PID 132, and if we write its maps out, if we write this out, we're going to see that we have a significantly larger number of APKs mapped into this process's memory. And the reason that this occurs is because the Zygote, basically every time you start a process, the Zygote in conjunction with the system server process forks a new VM. It also forks whichever application you're running, and then it gets mapped into its own child process. And again, this is all for efficiency purposes. So if we grep for APK files on this one, we see that we have many, many more. And these are all of the applications that are actually running on the phone. So what I wanted to show was, we have our Amazon application. Obviously, that's not necessary to run the phone. This is something that the user did, or it started up when the phone ran. And so if we look for Amazon within the process listing, and then what we want to do is, or what I wanted to show was, the system server is mapping everything, and then if you dump the memory maps for the individual processes, and as opposed to system server, they're just going to have their own maps. And this is And the reason that this is important is because when we do our memory analysis, we can't just like analyze the Zygote process, or we can't analyze the Android application in memory. We need to find each instance of the application to get the data structures that are there. The other thing you can do, though, is if you compare what, say you compare the variables that are in the Amazon Maps process, or you compare the code that's in memory, and then you compare back to the original, that would be like, say, in the system server process, you can see code that was overwritten or code that was changed. So it'll be changed within the Amazon process, but not within the data that's mapped into the system server process, and you know something's wrong. You know that a rootkit has overwritten memory. So again, if we grep APK on this, we see that the only thing that's there is the framework. The only thing that's there is the framework and then the Amazon APK, right? Because it's the Amazon, that's all it needs to operate. It needs the framework, which this is all like your base Dalvik Java classes. This is your HTC specific information, and then this is this is your actual application that you ran. So the whole point of this again was just to show that without kind of understanding how Dalvik works, you're going to get confused, or you're going to get the wrong results. Okay, so now that we have some very quick idea of how Dalvik works, the previous methods before we started our current project, these Dalvik instances were basically just treated as any other userland process. So I can dump the heap out, I can then run strings and grep across it to see, say it's the browser process. I can run strings to see if a URL is there. I can like try to file carve on the memory dump. I can run regular expressions across it. But this is like a very, I would consider like non-interesting from a research perspective, a non-interesting way to look at it, and it's also not very effective from an investigative standpoint. Particularly when you want to do deep analysis, it's almost impossible, because it's one thing to say, okay, the browser had google.com within the memory of the heap. But that doesn't tell me, was it in the bookmarks? Was it a page they actually visited? Was google.com like in the cache? Was it in the HTML of another page that was visited? It doesn't tell me the time it was visited. Versus if you do structured analysis, then you can say, okay, well that google.com string actually maps to the browser history. And this was the last time the person visited the website. And maybe the count of how many times they visited. It's a much deeper and I guess more formal analysis of the data, but the data you get out is much more useful to your investigation. Which leads us to new methods for Dalvik analysis, which is stuff we're working on now. And this parses Dalvik itself. So you have that libdvm in memory. And the same way we look at the data structures to get like a process list or the memory maps, you look at those data structures to see what's going on with that Dalvik instance. And what you can get out of that is all the instantiated classes. For every class you get the variables and the methods. And what's also interesting is you get the garbage collector information, which gives you sort of a structured way to look at previously deallocated objects, sort of similar to the way the KMem cache worked. So not only do you have what's currently going on with that application, but if you can walk the free list of the garbage collector, then you have an orderly way to get previous information as well. So how this relates to volatility is obviously volatility lets you automate all of this analysis. It puts the plugins, put it into a reusable way, so I can always use the PSList plugin to get processes and so on. So everything that we're developing for this is being built on top of the existing ARM support and volatility. And so you'll have these other set of plugins that can pull data out, pull the Dalvik specific data out, and then that's going to map to specific information inside of a running Android application. So that's something that, again, will come out a little bit later, but will be fairly interesting when it does. Okay, kind of talked about this already. This is just examples of stuff that could be in browser memory. One thing that's interesting to realize is if you look at your banking applications, they all, they're encrypting data on disk, or they're trying to do something cryptography related. Well, all of that's in memory now, and so if you can look at those classes in memory and figure out which one sort of controls the encryption or stores the encryption data, then the keys are just sitting there waiting for you to take them. So just as what would be a very small teaser, there's going to be a number of plugins that will be associated with this, but something that we're recently working on is this idea of you take a Dalvik instance, and I want to know every class that's loaded in there. So this is sort of like a cutting one view of that, which is you have this is the text message application. You have compose message activity.java. This is the class If you're used to Java programming, if you make these slashes to be periods, then this is sort of your hierarchy. So you have the compose message activity class, and then you have its instance field. So you have the receiver, the filter, the context, which is an Android specific thing, and then your signature tells you the type of that variable. So your code can then have the ability to parse those types and then pull the value out, and then you can completely recover that information out of memory, which is going to be very powerful when dealing with Android applications. So in conclusion, we have a number of new capabilities coming soon. The next release will have the base ARM support, which will let you look at the kernel plugins, and then the release after that will let you actually look at the Android applications themselves. So that will be, I don't know, a few months from now, but we're working on that currently. One thing before we wrap up and look at before I take like the final questions, I just wanted to do a few volatility links for people who maybe aren't familiar with the project or want to see what's been going on. All the plugins that I talked about, the Linux ones, are described in the command reference. That's our wiki. MHL put a lot of effort into updating the wiki, and it's very nicely structured now. We also have a page on the wiki called the Community Documentation Project, which is anytime someone who's not a core developer of Volatility blogs about Volatility, does a paper, has some research that uses it, we catalog that on the wiki. So you can see how other people outside of the couple developers, how they analyze malware with Volatility, how they're integrating into research. There's some cool stuff with sandboxes that people are doing now. And again, this is all documented on the wiki. We also have our own blog, the Volatility Labs blog. You might have seen it with the month of Volatility plugins. There's some very deeply technical posts on there. So if you want to really understand how some of the new plugins work and some of the new functionality works, read the blog post. Also, something that we'll be sending out to like a normal mailing list on Twitter is we're going to run a plugin writing contest similar to the way IDA does it. So you do your research, you send it into the contest, and the winners will get, there'll be cash prizes. You might get invited to speak at our annual conference, and it'll be a good way to get publicity for research that you might otherwise do and contribute to Volatility. So with that said, I saw some questions were flying by as I was talking. Please type in any other final ones, and I'll be going through them. Okay, so Dennis asked, will this be working on all versions of Android? That's our goal. We're getting a number of devices that span the different, what would be Android versions, which boils down to different Dalvik versions. So ideally we'll support, you know, the most used Android versions. So, someone asked, "How am I so awesome?" Not sure how to answer that one. And it says a few more people are typing, but I can't tell which window they're typing in, if it'll become a question or not. Okay, so obviously that wrapped up my presentation. I guess